Okay, folks. So we're into our week 5 lectures, I think. We're going to do some case studies here with the second order differential equations. Now, obviously, your assignment, VBA assignment, is also to you to do a case study, but I'll just warn you that these are second order, the ones that we're going to look at in this lecture. And your assignment is to be first order. What I mean by second order is the highest derivative is second derivative. So these are no good. Okay, so now I'm going to look at this. I'm not going to talk too much about it because I actually don't know everything about this. We'll probably just read what I have here. I can't pretend to be an expert on what the background of this problem here. I suppose the issue is this is kind of like a damper. It's a damped harmonic oscillator, but it's weird damping with this 1 minus x squared term. If I look at it, you see the sign is a bit weird from my point of view. Maybe we'll just say if this is damping, there's a possibility I've written the question down wrong as well. So if this is damping, we'll look at three regions. We'll look at x equal to 0, which is actually the same as x being less than, well, x is less than 1 in absolute value. So that means that in particular, x is between plus and minus 1. That's the first region. And in this place, we've got this damping. So the mu is presumably positive. I think it actually could go negative if I look below, but we'll assume it's positive. The 1 minus x squared is in this region positive. So if you add that term to both sides, this force is in the direction of the velocity. So I'm just, how am I going to write that down? So the direction of the damping is equal to the direction of the velocity. Now that's really weird. So when you're close to the equilibrium in terms of the spring force, you'll be pushed along in the direction of your velocity. So if you're heading towards the equilibrium, you're going to push past it. So it's actually a little bit like a spring, almost. But if you're, well, it's not like a spring, because if you're moving away from the equilibrium, you're going to be pushed further away. So it's really weird. That's the first case. At x, absolute value x equal to 1, so in other words, if x is equal to plus or minus 1, then the damping term is 0, no damping. Because the 1 minus x squared will be 0. And when the displacement is large, then what you're going to have is that this term here is positive, which means if you take it away from both sides, you're going to have ordinary damping. Well, I say ordinary, as in it opposes the direction of velocity. So it's really weird. There's probably so my feeling is that it's a kind of a thing that when you're close to equilibrium, it's very unstable, because if you move, say, away from the equilibrium, you're going to be pushed away. Then when you reach x equal to, say, plus 1, the damping's going to disappear. And then when you go beyond x1, what's going to happen is you are going to be you're going to be slowed down. And when you're so that's when your dx dt, it's really weird. It's actually going to have really cool dynamics now that I think about it. I didn't really understand it before. I feel like I'm understanding a bit better. Well, anyway, let's look at what we're looking at. So the important skill for us is to write the second order differential equation as two first orders. So the big story will be you introduce a new variable v, which is the first derivative. Now that's no problem here, because here this x is displacement. And what does that mean? Well, then dx dt is velocity. So we've got no issue. So that's our first equation. And what we're going to do is, if we differentiate both sides of this with respect to t, we get that the second derivative, the first derivative of v is equal to the second derivative of x. Okay, so we're going to have an equation for x, which is going to be this one, and an equation for v, which is going to be this one. And both of them need to come with their initial conditions. So let's write them down. So the first one is probably the easiest. Dx dt is equal to v. That's no problem. And the initial condition, we're going to suppose that the initial condition is x of 0 is equal to 1. That one's interesting because initially there'll be no damping. So it'd be cool here actually to plot the damping as well. Yeah. So I just paused the video, put in the yellow thing, maybe for next year for myself, to plot the damping to kind of explain what we did in the top right hand corner. Now, we also have a differential equation for V. Now, we could do it in one line, but look at this equation up the top. Now remember, mu is equal to 2. If you add the middle term to both sides, you get that the second derivative here is mu, which is 2, 1 minus x squared dx dt, which I can write as v in a moment, and then take away the x from both sides. So I found that the second, so that's just solving the thing above for the second derivative. It's 2, 1 minus x squared dx dt minus x. But of course, the second derivative, as I wrote here, of x is the first derivative of v. So I have dv, I have dv dt. Now, being able to do that is going to be important for you. dx dt minus x. And what's the initial value v? Oh yeah, I said I would put in, instead of dx dt, I'd put in v, because that's what dx dt is. And the initial v is also 0. Sorry, it's 1. Okay, so we're going to do some early approximations. Now I'm just going to go through this fairly quickly, just to kind of, you know, that you see some Euler's method, but really this is a case study. So yeah, let's go. Okay, so with the initial values of x and v, so let's calculate the next values. Let's see how we get on. So x1, the next value of x is equal to the previous value of x, which is 1, plus the step size, which is 0.1, times the previous slope. The slope of x is v, and the previous v is 1. So this goes to 1.1, okay? So what's happening there is, well, the velocity is positive, and nothing can really happen instantly. So if the velocity is positive, then the displacement is increasing. Let's see what's happening with v1. So with v1, I get, what does Euler's method say? It's the previous value, which is 1, plus the step size times the previous slope. So the previous slope is, the slope is this 2, 1 minus x squared. Now the previous x is 0. There's a confusion here, I mean, between the x and the t. I think that's probably fair if you have that. But anyway, the previous x was 1, times the previous v, which was also 1, minus the previous x, which was 1, wasn't it? So here I'm getting a decrease, because this 1, because x was equal to 1, we said that at that point there's actually no damping. So the damping term is 0, but the spring force is pulling it back. So we get this, if we bang this into the calculator or whatever, you're going to get 0.9. So yeah, so basically at this point, it's kind of moving beyond the equilibrium. There's no damping, but the spring force is kicking in and it's pulling it back, so the velocity decreases. Okay, so there's a bit of understanding there. Now we mightn't see anything interesting because the step size is such that it is. Well, anyway, I'll keep going. So the next x value is the previous x value, which is 1.1. That's not how you write 1.1, hey. 1.1 plus the step size, which is 0.1, times the previous v, which is 0.9. So here you can see that the velocity is decreasing, and so it doesn't quite move as far away. This time it doesn't go a distance 0.1, so you just get 1.19. v2, now let's see what happens and see can we explain it after that. So you get 0.9 plus, that's the previous v value, step size 0.1. Now let's look at this term. So you get 2 times 1 minus, what's the previous x? 1.1 squared, times the previous v, which was 0.9, minus the previous x, which was 1.1. Now I'm going to calculate this, and then we'll kind of just do some coloring in just to see, to explain what was going on. So I'm getting out of this 0, I get a big decrease in velocity. Now just in terms, we'll just do some coloring in here just to see what's going on. We'll separate those. I'll use a different color to get this previous x. So where was this previous x coming from? Here. And where was the previous v coming from? Here. So what we have now is as the displacement went outside the kind of, it's not even the equilibrium, the x equal to 1, we said what would happen here, there'd be this weird, there'd be ordinary damping. So it's going to, the velocity is going to be decreased, and it's going to be decreased in two different ways. So you get this ordinary damping, which is this first term here. So that's just ordinary damping. Okay, and then there's also the spring force, and both of them will reduce the velocity. We'll go again. So now the next one is x3 is equal to the previous x values of 1 point. Now remember, the velocity has been decreased, so we're expecting it won't go quite so far. What's the previous v? 0.7522. We can put that into the calculator. 1.19 plus 0.07522. Now we'll now start approximating. We'll just use 5 significant figures. So you get 1.2652. Now we're adding rounding error, but look, what can we do? V3, previous velocity, the next velocity. Now our velocity is positive, and we've got this damping, and we've also got the spring force. So the velocity is going to decrease even more. So it's going to be previous velocity 0.7522 plus 0.1, and now I expect the decrease, so it kind of went from 0.9 to 0.75. I'm expecting it to go down. That was 0.15. Expect it to go down even more now. It might go down as far as 0.55. We'll just see. So 2 times 1 minus the previous x value, which was the 1.19, times the previous velocity, which is 0.75. Now the only thing is, and we'll allude to it now in a second, minus 1.19, because the velocity is decreasing, this damping is actually getting smaller, but that's what you'd expect. But then the spring force is still going to be playing a role. So what we'd expect to see is that as we kept on going, let me just approximate this, the velocity will eventually reach 0, and then it'll go negative, and then it'll start coming back, and then you'll get kind of an ordinary damping. Yeah, we're going to see interesting behavior. I was trying to say I didn't understand. I kind of understand this more now as we go on. This should be 7522. Syntax error. Lovely. I'm getting 0.5706, and we'll just do 4 significant figures, 0. So what you'd expect to see, so if you kept on going, you'd expect to see the velocity to go to 0, and therefore the x to reach an x max, which would be kind of like an amplitude, and then the spring force will kick into play and the x will decrease, and then the velocity will go negative. So it says nothing particularly exciting. Not quite. I think it is exciting. Perhaps the x might grow until such time. Yeah, perhaps so actually that's not too bad. So we got a plot here of what's going on. Can we kind of understand? So let us use Excel and h equals 0. So I think we started with, so here's we can just zoom in here. Here is, we said that the velocity would go to 0. Now there seems to be a bit of disagreement between these two. Like surely, like dv dt, remember, sorry, dx dt is equal to the velocity. Now maybe there's just errors happening here. Like I'm basically asking the question, is that happening right above that? Maybe I'm just maybe my eyes are just a bit wonky, and actually it is happening. That now there'll be a little bit of error in any case, but look, it's more or less happening. So what am I banging on about here? So when the velocity is equal to 0, then the dx dt is a max. That is absolute rubbish, sorry. Let me use a proper color. X is a max. And it's kind of like an amplitude. Now we can see the amplitude is growing if you look. So this, say, if we call this the first amplitude, second amplitude, third, fourth, fifth, sixth, seventh amplitude, we can see the amplitude is growing. I'm not sure, is that something to do with error, or is that actually something to do with the system? Like there's this thing about conservative forces and stuff. Maybe this is a non-conservative force, so you actually would see an increase in amplitude. I don't think there's anything else interesting really going on, but I think it's kind of cool. Then you can do this. This is called a phase diagram. Occasionally there's differential equations that you can solve. You can't solve them exactly, but you can actually solve the velocity in terms of the displacement, and you can plot both of them. You get an implicit curve, so you end up with some kind of function in x and v equal to 0. And then that means if you did implicit differentiation, you can get like the derivative of, well, it's hard for me to say there. Anyway, something like that. I think you can do that with the pendulum. So we see this behavior. So here we see the phase diagram. I'm not really sure. So it says it has a limiting behavior. I'm not sure. So maybe the amplitude grows and you get some kind of thing. We can probably go beyond that. Hopefully it's somehow interesting. And it's a kind of a serious problem we can look at. Okay, let's look at another example. Predator prey. So think about, what's the one we used to learn about? Rabbits. Well, we had a Russian lecturer in college, and he was going on about, we thought it was about cows, but it was actually chaos, what he was saying. But rabbits and foxes. Yeah. So think of this is the fox, and this is the rabbit. And the idea is that if there's loads of foxes, the rabbit population decreases. Let me see. So let's look at this differential equation and see can we kind of understand what's going on. So this is the rabbits, and this is the fox. So how can the fox get into trouble? So basically this interaction. So imagine, like, if you want there to be lots of foxes and rabbits around, if there are, you're going to have lots of interactions. You're going to have lots of foxes eating rabbits. And so the xy term is the interactions. So the idea is that if x is small, so that's few rabbits, or y is small, few foxes, or both small, you won't have, in any of those cases, many interactions, you won't have foxes eating rabbits. But if both x and y are big, so lots of foxes, lots of rabbits, you're going to have foxes eating rabbits. Okay, and if this is big, okay, that's that argument. So then a proportion of the interactions are going to lead to, this is eating rabbits. Now, when the foxes get to eat, they're going to breed. And so this is baby foxes, basically. Now, the other issue is that the rabbits can kind of eat loads of grass and stuff. So basically what happens is if you've got rabbits, if X is big, you get more rabbits. So these are baby rabbits. And like, it's kind of saying that you're not really going to worry about the rabbits running out of food in this model. But what is an issue is if there's too many foxes, then that is an issue. There's competition. And it doesn't matter how many rabbits there are, it's kind of saying, kind of. So this one here is starving is probably not right, but anyway, dead foxes. So this is what are called coupled differential equations. It can be used in different things. So one particular example is use these parameters. So the alpha, beta, delta, gamma. So here you see, this is the kind of cool stuff you can see. So this one is using Euler's method. This one might be this isn't an exact solution, the phase, but you might actually be able to find the exact version of the bottom thing. Okay, so here we see, so x was the, which one was x? X was the rabbits, wasn't it? Well, let's say prey. And these yolks are the predators. I should keep with the foxes. Rabbits. So when the, so let's see what happens. So when you get a boom of rabbits, rabbit boom, then what can happen is that the foxes can start doing well. And there is a lag behind it. So the foxes reach their max, peak fox. Now, when you reach peak fox, as what's happening is in this window from rabbit boom to peak fox, you can see that the fox is starting to eat more and more rabbits. And so the rabbit population decreases. And when you reach peak fox and rabbit population has gone down, and here you can see kind of there's a bad point where they match actually, then the foxes suffer because there's too much competition. That's a problem for them. And also it's kind of related with there's not enough rabbits around. And so the foxes actually die out. So here's your collapse, fox collapse. When the fox collapse, now they don't quite go extinct. The rabbits never really go extinct. The rabbits can recover, and you get into the same story again. Now here you see this is a plot of predator versus prey, and so you again, this may reach equilibrium, I'm not sure. It's just another way of looking at this picture, and it's just, I know sometimes you can find these phase diagrams, you can solve them exactly even if you can't solve exactly for the other things. So the idea would be that this is an equation, x and y equal to 0, but the time is just lost. I think that's the idea anyway. Okay. Right, and then the one that's interesting for us is the pendulum. Okay, so consider the angle theta that a pendulum linked L with an object of mass m makes with the horizontal. So you can do some kind of stuff here. You can just do your normal trigonometry to show that the magnitude of this is mg sine theta. And if you so what you do is you work in different coordinates. You don't work in xy coordinates. You work in theta r coordinates. I don't know if you do that or not. So now r isn't going to change. It's only theta that's changing. So it's like a moving coordinate system. So this little pink thing might be theta hat. So that's kind of meant to be kind of 1 in the theta direction. And of course, as the pendulum moves, the basis vectors as well. So it's like theta hat versus, actually I shouldn't say x and y even though it's right. So really what I'm talking about is like I hat, j hat, I j case, yeah. So the force in the pendulum, so the only forces that are there is the gravity, and it's only this part of it, mg theta, theta hat. Now possibly that should be minus, plus or minus, I'm not sure. That does anything. Like the other gravity, part of the gravity doesn't do anything. Okay. So the force on the pendulum is missing the tension force, but as long as the angle doesn't get too large, this is balanced by mg cos theta anyway. It's going to be balanced all the time because we're not going to have a string here. We're going to have a rigid yoke here, so there'll be no bother. So the only force to the tension of gravity working in a different coordinate system, as we said, writing down Newton's second law, you can show, I won't go through it, is that where alpha is the angular acceleration, so that's the second derivative of the angle, and everything here should be in radians, you get that this is the pendulum equation. Yeah, so usually the small angle approximation is made. You can talk about the Taylor series to see how this is accurate. So you can look at theta, sine of theta, excuse me, is approximately, actually let's do an equals, is equal to theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus dot dot dot. And the story here is like the angle maximum is going to be whatever pi over 2 or whatever, or even pi, wouldn't it be? Where is the angle with the pi? Yeah, so it could go up to 180 degrees. So the maximum of the theta is pi, so like 3, but the numbers on below these 5 factorial, 7 factorial are really, really big. So these terms basically are quite small. And if you keep the angle kind of less than 5 degrees, which is about 0.1 of a radian, there's so like say theta is 0.1, then theta cubed over 3 factorial is very, very small. So in fact, I've said that this is approximately theta. That's nonsense. This is approximately 0. And if you want to keep theta small, this is, I did it again. Sorry, I'm a bit dopey today. 0. Then this is approximately 0. So what you get is, in fact, that sine theta is approximately theta. And usually that's how the pendulum is made. So this is if you keep theta kind of less than 10 degrees, or maybe less than 5 degrees is something we looked before. And then so you approximate the differential equation and you can solve that exactly using the Laplace transforms or whatever. But what if you want to look at larger angles? So then you have to use a numerical approximation. So we're going to do this. So taking length of 98.1 centimeters, just to keep the numbers nice. Assume the pendulum is released from rest at an angle of pi over 2. So we're going to have it's going to be kind of sideways, if you know what I mean. Like this angle here would be 90 degrees. And this is what the differential equation looks like. So you start by saying let V be, so you always let V be the first derivative. Now we could, if we wanted to go in context, we could have used omega. If you ever seen omega in a formula, that's what it is. It's the angular velocity, the time derivative of angle. But anyway, so this is like your first. Now I think we're going to, on the next page, we'll probably put them both together. We'll look at that stupid joke on the next page. So we get, if I put them both together, I get the derivative of theta is V, and the initial value of theta is pi over 2. And then look at the second equation here. So the second derivative of theta plus whatever. So the second derivative of theta, so if I differentiate both sides here, I get dv dt is equal to the second derivative of theta, and then take away that 0.1 sine theta, you get that this is minus 0.1 sine of theta. So you get that dv dt is minus 0.1 sine theta. Obviously, there's one thing I forgot to say. On the previous example, we didn't have to do this. So what we end up here is a system. Let me just finish this off. V of 0 is equal to 0. You end up with a system of like simultaneous differential equations. But the predator prey, it's not a case of theta and its first derivative, theta and v. It's two kind of totally independent things, but most of the time we'll be looking at this kind of thing. So here's the stupid joke. So there's a joke that engineers think that sine theta is equal to theta, which of course is it's only an approximation. Is that funny? I shouldn't try and be funny. Right, so here we're looking at Hein's method for the previous thing. Now I haven't done any of this by hand, so let's see. So we put in the initial value of theta, that's the pi over 2, and the initial velocity, which was 0. We calculate the two predictors. So this one here should be doing v predictor is equal to the previous v value, which is 0, plus the step size, which here is 0.01, times the derivative of v. And the derivative of v is minus 0.1 sine of theta. So this is minus 0.1 sine of the previous value of theta, which is pi over 2. And sine of pi over 2 is 1. So you get this value, the minus 0.001. Okay. And then you do the theta predictor. So theta predictor is the previous value of theta, which is pi over 2, plus the step size, which is 0.01, times the previous value of v. The previous value of v is 0. And so this is kind of saying if there was no velocity, it shouldn't change. So you get the same thing again. Then we go into, maybe we'll just look at this green cell, highlight it. That's up here. So this is now Hoyne's method for theta. So this is, oh crap. I'll just write theta 1. So you get the previous theta value plus the step size, and then you average the two slopes. And what was the derivative of theta v? So you average these two, the red box and the purple box. So the previous v plus the predicted next v. And then the last thing we're looking at is this number here. Let's get this out. So Hoyne's method says the next v value is the previous v value, which is 0, plus the step size, which is 0.01, and then you average the two slopes. The derivative of v is minus 0.1 sine theta, so you get minus 0.1 sine of theta. The previous theta was pi over 2. The predicted next theta is also pi over 2, so that's in cell C3. So there's two slopes, and I should average them out by dividing by 2, and so you end up with minus 0.001, and you keep on going, you get something like this. Now I should really have done more time, because what you'd see is you wouldn't see, you saw before we did this and there was errors, and that the amplitude was, there was differences between the true behavior, well, the approximate true behavior here, and the one where you use sine theta equal to theta. So have we got anything interesting up here? No, here we got a comparison. So a pendulum with a large angle is a much greater period. So if you imagine a pendulum with a big angle, so basically what's happening here is, I think maybe you'd be better off actually just watching a video for this, but you get this kind of phenomena where it kind of takes it ages to come down, so it has to kind of move. So basically the problem is, when you do sine theta equal to theta, it's like the pendulum is just moving like that, but of course it has to actually go in a big circle, so you get this kind of a delay. So this is the theta, sine theta equal to theta approximation, and it kind of thinks that the pendulum will go much faster than it does, whereas this is the using, now this is an approximation, so it's a different approximation, but it's far more accurate. What am I pointing at here? Well, obviously the blue one. So this is the Hoyne approximation instead. Now they're very, very different things. Very, very different things. The sine theta is just not valid. Not valid. Anyway, valid for initial value of theta being much bigger than 0.1. So that's the problem. So a pendulum with a large angle is a much greater period than the simple analysis suggests. So yeah, okay. We could also add in some air resistance, and that would be interesting. You would see the amplitude decrease over time. So another thing that happens is you get error and chaos, which I probably shouldn't go into, because it's just, we just want to say we're going to be careful. So what's going on here is that you have sources of error. So you've got truncation, crap methods, rounding, crap computers. So this is poor methods and poor computers. There's an additional complication, which is that you can have chaos. Now what chaos basically means is a small difference at the start can make a big difference at the end. And that really makes the truncation error and the rounding error really, really bad, because it's saying that if you get a little bit away, a small error, like even to like in the 100th decimal place, you get very, very different behavior. So if we're doing numerical analysis on chaotic systems, we can't really do it. It's nonsense, because we're adding an error and a little bit of a change changes things utterly. It's the same reason you can't do weather prediction beyond 3 or 4 days. The issue is, so here's a fact about the equations they use for weather predicting. If you change, say if you think the temperature is 10 and you run the model, you get something. If you change the temperature to 10.000001, after 4 or 5 days you get totally different behavior. And then the issue is that you just can't predict weather, because you can't predict the atmospheric conditions accurately enough. So, and that's not without mentioning rounding error in the calculations. That's without mentioning truncation error. It's just doomed. So you want to be very, very careful here. Now it turns out that actually with the pendulum has chaos, but it's about where it's if you start it upright. So I think there's a video here if you want to watch it, and you'll see if you start this is a double pendulum, is it? Oh yeah. So the real pendulum, the only problem is, so say this is the initial point. So if you start it up here, so if you change the initial angle very, very little, so this is 180 degrees, that's pi. So if you go to pi plus 0.0001, it's going to go off in that direction. If you do pi minus, it's going to go off in that direction. And very, very little small changes in the initial condition will give you very, very different answers. So it's not that bad. So actually we can look at the real pendulum. Now, what's totally different is the double pendulum, where everything is chaotic. So you can write down the differential equations. You can kind of solve them, exact solutions, but the problem is if you can't measure the initial position of the pendulums to infinite accuracy, which you can't do in the real world, your solutions very, very quickly go mad. So all very, very interesting stuff. Okay.